Good afternoon, everybody. For those of you who do not know me, my name is Ali Kujuri, and I'm a adjunct professor at the Department of Engineering Science and one of the organizers of this lecture series. On behalf of the department and the School of Science and Technology, let me welcome you all to this 11th lecture in this academic year, and also the 98th lecture in the series since we started in 2006. Before, I would like also, by the way, to thank Ajlan now T-Site Technologies for sponsoring this lecture series since the beginning in 2006. Before we start the lecture, I introduce our invited guest. Let me mention that we have ordered pizza, which is going to arrive at 5:30, right after the lecture. And then also the next lecture will be, let me just click on here, will be on April the 16th, titled Augmented Phonocardiograph Acquisitions and Analysis by Dr. Nancy and Dr. Todd Reed, Departments of Computer Science and Electrical Engineering, University of Hawaii at Manoa. And they are currently visiting the Computer Science and Engineering Science Department, respectively. Our guest speaker for today is Mr. Jim Eyer, and the title of his talk is What is Signal and Power Integrity in Digital Systems, and How is it Changing our World?
Good.
It's yeah, that's pretty close there.
Okay. Mr. Jim Eyer's entire 30-year career has been involved in energy efficiency, renewables, and advanced energy technologies, concepts, benefits, and markets. For the last 20 years, Jim has focused on energy storage with an emphasis on benefits and value propositions. Jim owns and is a principal and senior analyst for E&I Consulting. He's senior advisor to the California Energy Storage Alliance, and before that, he was senior analyst with Distributed Utility Associates for 13 years. And before that, he held a range of positions with Pacific Gas, an electric company related to advanced electric technology and concepts, research and development, energy supply planning, and commercial energy efficiency services. He has an undergraduate degree with a double major in physics and management from Sonoma State University, and also an MA degree from the same university. So here is Jim.
Thank you very much. That was quite an introduction. I wasn't sure he was going to read that all off, but it does illustrate a point that I think it's important is, to a large extent, what I'm going to talk about today requires kind of a broad, some good breadth in what you know and what you can do. You don't have to be an expert at everything, but a lot of the new things going on the energy side really require a fairly broad perspective on things. And that's fortunately, I had the opportunity to get that here at Sonoma State. So not to talk too much about the introduction, we're going to get into the utility of the past, talk about distributed energy resources, kind of a new and fun topic that's exciting, disruptive, and so on. Introduction to smart grid. We're just going to talk a little bit about what it is. There's a lot out there on the topic, but I think we can help you at least get a handle on what the key elements of it are. And then kind of bring it all together into the electric utility of the future, talk a little bit about what that might look like. And then I like to dwell on this technical-business nexus. I've spent my whole career there, and I like to tell people the engineers really are too impatient to deal with business people, and business people are too intimidated to deal with the engineering or technical people. So it's actually kind of a fun place to be, a little maddening and frustrating sometimes. And then I'll touch on some thoughts about career possibilities. But this will be high level and fast paced. I looked at some of the subjects of your other lectures. They're a lot more focused and detailed. So this is going to be very high level. I'm certainly willing to answer questions, and I'll be leaving a soft copy of this with Dr. Gajori. So it's unfortunate that I have to start with something like this. You guys may not need it, but there is a difference between energy and power. And when I say that to people, they're kind of, they don't quite get it. But on the left side, I have some characteristics or features, if you will, of energy. And on the right, I have power. So we talk about the physics, its work, amount of work accomplished or generated, or energy generated. It occurs over time, and it can be stored. You can store energy. But over on the power side, it's really the capacity to accomplish work, if you will, the rate. I mean, it's an instantaneous, and you can't store power, by the way. But then there's this whole area of the finance, if you will, where the dollars are. So on the energy, you've got fuel and variable maintenance, operating expenses, variable costs, so on. So these are all the dollar signs, if you will. Shorter term commitment, relatively less risky. These are all kind of important from the business standpoint. And then on the right side, power is an investment, infrastructure. It's a fixed cost, lasts a long time. You have to add it in chunks. You can't just add a little bit of a wire capacity. You purchase it with capital. It's not an expense. Long-term commitment, relatively more risky because it's a long-term commitment. So I dwell on that. Amazingly, I've given that slide in a room full of PhD physicists. So, okay, so some have said the electric utility is the largest, most complex machine ever. It's pretty reliable. It doesn't break a lot. I mean, if you look at the numbers, it breaks now and then, and under extreme circumstances. The technologies are very familiar and mature, and I say very, I didn't put it there, but generation is mostly boiled water, oil, gas, natural gas, nuclear. It's burning some plant matter and a little bit from the earth, but mostly familiar fuels there. Transformers for voltage conversion, they have incremental improvements along the way, but they're pretty much like they were before. Wires, they haven't changed a whole lot, although there's some innovations there as well, the way they're manufactured and different cores so nonetheless, a wire pretty much is a wire. Capacitors for reactive power management, those haven't changed a whole lot. So they also use a lot of established methodologies to assess these things. So a lot of it's very familiar. Limited innovation, I missed that one there. Because of the characteristics that I just described, there's really no need and no driver of innovation in the electric utility industry up until somewhat recently. So this shouldn't be any surprise. You start at the top with the generation normally, put it into a step-down transformer to go in, a step-up transformer to transmission. Then you do a sub-transmission or something in between, and then you take it to the individual places where the energy is being used. That should come as no surprise. So again, steam-based, Rankine cycle. We talked about the fuels. A limited focus on environmental effects, or as the economists call them, externalities. Nor was there emphasis on sustainability. If you can rip it out of a mountain and throw the dirt back over that or into a valley, fine. Increasing generation economies of scale. I'll touch on that a little bit more in a minute. Supply must match demand almost exactly. I'm sure you've seen pictures of the control center where they have big screens and everything. It's like a war room. They got to match supply and demand at all times, almost exactly, within less than 1%. Otherwise, the system can have big problems. One-way energy flow, top to bottom, kind of dumb. There wasn't a whole lot of digital or computational or smarts in the system. Pretty much all mechanical. You just build it a little bigger than you need, concrete and steel reinforced. And then this lumpy capacity additions, that's a big deal. You can't add a little bit of capacity to a transformer or a wire. You have to take out the old one and replace it with a fatter one or put another one next to it. And that's relatively inefficient from an investment standpoint. And then very little energy storage, less than 1% of the capacity has ever been storage. So I think that'll change, obviously. So the business, it's vertically integrated, goes all the way from supply all the way down to the service. It's a natural monopoly, something the economists would talk about. You don't want 8 sets of wires running everywhere. In the utility realm, it's kind of an odd business model. The profit they make is strictly regulated, and it's really a return of an authorized rate of return on an investment in a piece of equipment. So that's how they make money. So for example, they don't make money on the energy. They merely make money by installing equipment and getting their authorized rate of return on it. And I don't know if that means a whole lot to you, but it gives some perverse incentives to do things like build stuff and not necessarily conserve fuel, for example. I'm generalizing, but in a gross sense, that's the case. So very conservative, limited innovation. There's no reason for them to even think about taking on new technology risk because they don't get any special incentive if they do that and something good happens. And if something bad happens, they might get fired. Boring. I would never suggest this industry to anyone. But things are changing, and the change will make it very exciting. So just quickly, on the concept of economies of scale, one of the drivers of the lack of innovation was the fact that there seemed to be constant improvement in the generation technology. And a lot of it had to do with the thermodynamics of going to a larger facility. So you can see starting in 1945 through 1985, the amount of capacity that was installed is getting bigger and bigger. Each chunk is getting progressively larger to the point where we sort of level off at about 1,200 megawatts. And there's thermodynamic limits at the top too. And apparently that's what that's about. I'm not a mechanical engineer, but that's what I've been told. So what you see here is you got that increasing scale, and then it leveled off starting at about the 70s. And we had a similar phenomenon in fuel efficiency. That's part of why they went to those larger plants. And then eventually it leveled off again in approximately the 70s. And then finally, you can imagine what that did to price. It was constantly coming down, so there was never any strong reason for them to try to innovate because this economies of scale thing was kind of innovating for them. And eventually it leveled off again in about the 70s. Most nuclear plants, for example, are about 1,000 megawatts. So we went from this vertically integrated silo approach to the utilities, and these folks rarely had to talk to each other. And we're going to go to what I'm calling a multifaceted business model. They're being drug kicking and screaming to it, but technology is driving this change for the most part. So it's multifaceted. You kind of got the customer in the center there. You're going to have energy flows going all over the place. Same with data and information, and even intra-utility action. And that's part of where the smart grid comes in. So it used to be a little bit of communication upstream, just enough to tell the generators how much to turn on or turn down. That was kind of it, but that's not going to happen anymore. It's going to have to be a lot richer than that. Quickly?
Yeah, that slide you had before, was that the average generator size for gas?
It was the more,
generation?
well, I can't remember. That one may have had both average and marginal, but nonetheless, it's the trend that's important, that it's going up and up, the size.
Mm-hmm.
So this is in megawatts over here.
Yeah. The
So
average generation was like 500 megawatts.
Yeah, so I should know my own chart, but so the average was going up as well, but the marginal plant, the new stuff going in, was going up even more dramatically, but it did level off.
Mm.
So forgive me, I'll have to
Thank you.
go. Move back through that. All right, so we went through this. That's really a powerful thing to remember. This is really where the model's going, multifaceted, intra-utility, all over. So what's that electric utility of the future look like? Well, unfortunately, they're not going to rip the whole thing out and start over. So what we're going to see, at least for the next 10 or 20 years, is they're going to superimpose new stuff over the old. So we've already seen a lot of renewables going in at the bulk level, if you will. And now there's a huge interest in storage. There's actually been some energy storage through the years. If you look it up, you'll find there's some fairly large pumped hydroelectric storage plants that have been in this for a while. But beyond that, we're going to start to see stuff out in the periphery, both, generation, renewables, and storage. We're going to need much more intelligent, I'll just leave it at that, infrastructure to handle all that, because remember that one-way flow before, that was relatively easy to manage. But for example, the transformers weren't designed for two-way flow. So if you have too much energy generation down here, and it has to go back up through the transformer, they're not really designed for it. It can be fixed, but one thing you could do is add storage. Another could be to refurbish or redesign your substations, but utilities are reluctant to do that. And then there's this concept of the microgrid coming in. That just means that parts of the grid can sort of be autonomous, can be like little miniature grids. They could be either still connected to the grid up here, or in the case of emergencies, this thing might be able to run on its own if there's enough power and energy down in that part of the grid. You can't do that without the smart grid. And I do have a list over here of kind of some key parts of it: sensors, monitoring, data, communication, computation, control, and security. I'll touch on that a little bit more detail in a few minutes. But a lot of that's not there yet, and it's just being developed, just being tested and conceived of. Distributed energy resources, one of my favorite topics. So we're just talking small modular technologies added to the grid at or near use. Emphasize at or near use, as opposed to from top to bottom like before. Instead of that model of central through generation or bulk generation to T&D, transmission and distribution. For one thing, it enables this more optimized infrastructure. You can build to the situation that you have in a particular part of the grid rather than using generic top-down approaches. You can add this capacity just in time, which you can't do, like I said, with wires. That's a nice feature. Modular generation, modular energy storage. You can also target what's called demand management or power reduction to specific parts of the grid where you're having challenges. The utilities would never have done that in the past because then that's less revenue for them. But all that means is if you can turn things down in a part of the grid that's overloaded, that's almost maybe even better than turning things on. So that's become a really important resource in the last even 10 years. And there's nothing saying you can't target energy efficiency at the same thing, at the same challenge or same part of the grid. If you're going to be able to cut the maximum power draw down by putting energy efficiency in, that may be the best, most efficient, most efficacious thing to do overall. All right, so what about generation? Just talk about that quickly. We still have advanced reciprocating engines, and they're getting better all the time. They're not the stinky old polluting things of the past. You can run them natural gas through them, biogas. You can actually run hydrogen in these as well. There's a professor at Cal doing some work on hydrogen engines. Actually, that's a fun digression. Hydrogen is an expensive energy carrier. It's expensive to make it per unit of energy out from an engine. But a lot of times you only need the thing to run a few hundred hours a year, let's say. So what you're doing is you're using the engine in lieu of, for example, a wire upgrade. And you only need to get that last little bit in the hot summer days. It may actually be that an engine and hydrogen can do that less expensively than upgrading a big transformer wire substation. So that's an interesting possibility. Clean diesel engines, 95% cleaner than the ones of just 20 years ago. Advanced turbines, things called microturbines in the tens or hundreds of kilowatts. Fuel cells, I'm sure you guys have heard of those. Photovoltaics, small wind generation. Those are actually kind of impractical because you got to get those up, but people are still trying to sell them. You need height. Combined heat and power, and combined cooling heat and power. These are all alternatives on the generation side. Energy storage, there's really kind of a large spectrum of possibilities. I'm not going to go into details here, but just suffice to say, there's a lot of different technologies or approaches you can use to store energy, and they all tend to have kind of their own unique set of characteristics and advantages and disadvantages. So there really are these things going on. Electrochemical batteries, there must be hundreds of these things now. If you just scour the internet a little bit, you'll find there's many chemistries that are being evaluated now. Supercapacitors, they can store a lot of joules. Compressed air, there's both large and small examples of this, some as small as 100 kilowatts, where you store the compressed air in pipes, like natural gas pipes, and then hundreds of megawatts where you store it in underground caverns of various types. Cold storage, this happens to be something called an ice bear. What they do is they make cold at night, and then they don't have to run their compressor during the day, which is actually a big power and energy hog. Not this, but the compressor real time. Flywheels, these things are really fantastic. I used to laugh and think that was kind of silly, 15,000 RPM and all this other stuff. Things work, and they work really well, and they're efficient, and they're reliable, at least so far. Superconducting magnetic energy storage, pretty far out there, but it works too, and there have been demonstrations. There was a demonstration of that a few years back. And hydrogen, you can always make hydrogen and store that. Just quickly, a little point about flow batteries. Normally when you think of a battery, you think of a self-contained thing. All the chemicals are in there, all the mechanics, the parts needed to do the oxidation and reduction, they're all in one unit, and if you want more energy or power, you have to buy more of these batteries. Well, flow batteries, using various chemistries, you separate the chemicals from the actual machine so that you can scale them independently. And these have some very interesting possibilities too. There's a lot of folks working on this concept. So, and it makes, for example, if you want to be conservative, you can always add more energy later to the thing. With these, you have to build a new building, build more racks, and so on. So don't want to dwell on that too much. So some notable features. Again, these things are more optimizable for various circumstances. They use a variety of fuels. There's a good diversity. I think I showed you at least a dozen different possibilities, and there's more. They tend to be pretty clean, and even if they aren't, they won't be cited. You've got to have permission to put those in. The more units you have, the more reliable you are with the unit diversity. Some of them are transportable, so you can move them around when conditions change. Can't do that with a wire. Some have direct current output. I'm just calling that out for some of you folks here who might want to take a look at that. I think there's going to be a resurgence of direct current stuff going on in the next 10 years for a variety of reasons. In some cases, it makes sense. But to use it in an AC system, you need power conditioning. So I don't know if you're familiar with this term inverters, but they're the things that take a DC and chop it up and make it into an AC and vice versa. So these are key ingredients of photovoltaic systems and battery systems and fuel cell systems for that matter, which all do DC. And modern power electronics, it's really exciting what's going on. I mean, it started when I was going to school, and it's just gotten to be really exciting. Just a couple of key themes when it comes to why these things are good or what makes them good. The closer you get to where you need the stuff, it's more valuable. In part because you're offsetting the need for more stuff upstream. The closer you can get the stuff to the end use, the less you need upstream to manage that. And it's not as straightforward as you might think. For example, transmission and distribution systems sometimes lose as much as 10% of the energy. Well, that tends to be during hot days when the wires are hot and things are heavily loaded. Well, that means you need 10% more generator upstream to get the same amount of energy to the load. So there's implications all up and down just from that one consideration. So getting close to the load is really a good idea. By the way, I'm generalizing. I believe you need both, the bulk and the distributed. They complement each other, and I don't even know if I have that point in here, but I really believe that. Higher cost than bulk generation. Economies of scale, if you have to build 10 things instead of one thing, you got to get it permitted. Transaction costs, hassle, it's just going to be more expensive. Fuel costs, getting the fuel there. Nonetheless, you really need to, this is a mindset thing that I encourage everyone to try to get, this sort of benefit cost thing. You got to compare this high cost thing to the alternative. And if you can avoid the need for an upstream big generator and transmission and distribution and some other stuff at the end of the line, it may be that that's still better than doing the other one. Today, the utilities have the incentive to do this. And that's changing, but that's the way things are today. It's riskier, new technology. I put that word in quotes. I think it's riskier to not do it, but that's what they would say. It's new and improving, not familiar. You don't have the experience, the tools. This is another thing. That the power engineers have always used relatively simplistic tools to do their circuit analysis. And well, if you have things going all over the place instead of one way, you can imagine how much more complex that's going to be. And we're just seeing that now with the solar. I mean, it's really challenging to get in there and analyze a lot of disparate things, especially things turning on and off. Financial uncertainty. You never know if these things are going to go 5 years, even though someone says they're going to go for 20. So, there's definitely more than this. In fact, this is not driving technology development. It's probably everything else. Mostly vehicles at this point, but also things like that microgrid thing I talked about, and even development in developing parts of the world where they're starting to look at some of these more modular technologies, batteries, wind, photovoltaics, and all of them as a way to leapfrog the old model with the wire that distributes out to the periphery. So it's a totally new way of thinking for utilities. I hope that came across. Unfortunately and fortunately, it's very disruptive. As far as careers go, I think it's a neat time because these guys and gals are feeling their way in the dark, as are the regulators and as are the vendors. I mean, this is new ground, but it's kind of an interesting time for innovation, new thinking, learning a lot of stuff, but it is very disruptive. I'll try to cover my butt a little on the comment about the guys. It used to be mostly men, and a lot of those guys are retiring now. There was a period of time when there was very little hiring in the utility realm for various reasons. So what happened, and it tended to be older white guys that were left, because that's just how things were in those days. But they're retiring now, and there's a need for a lot of fresh blood that has good, solid engineering background as well. So they're hiring a lot of MBAs, and those guys don't know what they don't know. You guys don't suffer from the same plight, I hope. So much more complex planning. I could have put much more complex, like 3 or 4 orders of magnitude maybe. Control and operation, much more complicated. It enables the competitors. Utilities are risk averse by nature, but it is going to economies of manufacturing. So making lots of pieces instead of making one giant one. So instead of economies of scale, facility scale, we're going to economies of manufacturing scale by making lots of little ones. Just quickly, again, this is kind of a mindset thing, but imagine you're the power engineer. You've got a piece of equipment that's rated at 12 megawatts, and in the next couple of years, you can see that you're going to have an overload here. Well, this lump solution, there's your overload there. The lump solution is to add that much extra capacity, a third or more, depending on where you are and the circumstances. And the utilities have never had any other alternative, except sometimes they would pay people to turn things off if they were getting right close to this thing, but eventually they would just pull the trigger and build a new thing. If nothing else, they got their rate of return on that, so they were perfectly happy to do that. The distributed resources now means you can play much closer to the margin. You can maybe wait till later and do it, the upgrade later. It may turn out that this goes away. I mean, if you have economic hard times, electricity use may go down. So if there's uncertainty there, you can do it. But that is an incredibly much different mindset. We'll leave it at that. So what the heck is a smart grid? Unfortunately, you see stuff like this when you ask the question. And that's not very helpful. I mean, if you want to spend 45 minutes looking at this thing, it's got some good stuff in there, but I like to kind of break apart the pieces and lay them out on the table a little bit in a little bit more simple fashion than that. So certainly information, near real time and historic, communication, controls, which helps with automation, sensors and monitoring, computation, including data management. Maybe that's a misnomer. It should be data mining management, so on, but I mean that in the broad sense of the word. Some very sophisticated algorithms and visualization. The people operating the system need to be able to see that. I left security till the last, but generally they start there. They don't want people hacking into this and being able to do dangerous things especially, but that's a really important thing. So that's kind of the key elements of it. Functions, again, the distinction maybe is a little blurred between a function and a feature, but part of it is this advanced metering infrastructure, which allows, everyone's heard of smart meters, so it allows much more detailed and precise aggregate data about what's going on at the point of use, which they never really had anything close to that. It allows for richer price signals. It used to be just one price all the time. Now they want to go to two, but at least in theory, you could charge real-time pricing with this, with smart grid. Demand response, that enables that thing I told you where you can turn things off. There's a lot of that going in now instead of power plants, and only smart grid's going to allow for that in a big way. Increasingly sophisticated SCADA systems. Again, they used to be mostly mechanical with a little bit of communication and some hard wiring, but now it's getting a lot richer. These things called synchrophasers or phasor measurement units, these are really exciting. They're pretty arcane things, but they allow for synchronized aggregation of real-time data so that operators can get in there and look at the system and move things around and all that, which they could never do before. A lot of automation going on at the transformer substation levels. Dynamic thermal rating of equipment. Used to be the engineers would just say, what's the very, very worst case? And then they would never use the equipment past that. Well, now you can do a dynamic rating and make better use of that equipment on the margin. Monitoring and telemetry. Situational awareness. This is the biggest sort of benefit, if you will, that people call it out. It seems so rich and powerful. It's surprising it hasn't been done any better than it has in the past. But here we go. So we're going to be able to give good situational awareness. Notice I said present and future. It's important to do things like trending and being able to go out even a day or two and kind of figure out how you might move things around today. So it's not just real time. It's also projections and forecasts and things like that. Optimizing various pieces. Looking at both cost and benefit. The model in the past looked at cost. How much does it cost to do something? Well, now you can balance the benefits more because you now have the infrastructure and communications to do that. Energy delivery, use efficiency, so you can make that more optimized. You can take better advantage of the capacity you have, both in terms of the existing and what you need to add to the system in the future. And then this concept of asset utilization, trying to get more energy, more kilowatt hours through the same kilowatt. That's improved asset utilization, and the dollar people like that. Distributed and variable output resources. Without smart grid, it's really challenging to, you can't even imagine controlling hundreds of these things, and then some of them have output that varies, and you don't know when it's going to vary, solar in particular, and wind as well. Customer service, power quality. Used to be everything was the same. Well, some customers need better power quality than others. Being able to take the environment into consideration, that was pretty much never considered. Well, now that they can and will. I talked about microgrids, so we've got automation and then that autonomous operation. There's no reason why parts of the grid can't isolate themselves. Islanding is the term they use, and those can operate on their own. And then this thing about self-healing grid. So instead of having to send, 3 guys and gals out to flip switches and look at things with flashlights, they can get this thing to have the smarts built in to do some of the diagnostics and response. And then again, microgrids. So utility of the future, well, we're definitely going to have more sustainable, diverse fuel resources. That's obvious. More efficient generation, more diverse generation technologies. More emphasis on what's called combustion turbines or gas turbines or expansion turbines. Brayton cycle is the technical term the mechanical engineers use. These are getting pretty sophisticated, and they're based on airplane engines, which have to be efficient and robust. So we're seeing more and more of that now. More variable generation, renewables. Managing both supply, and I talked about demand management. Some people use the term megawatts, so turning things down or off. And then using energy efficiency tactics. There's one that the utilities use now called conservation voltage reduction. So they're always trying to tweak the voltage so that the energy losses are as low as possible for any particular circumstance. Gets back to that dynamic thermal rating. So utility of the future is going to definitely have smart grid, all those sensors, all those things that we talked about already. More distributed resources, modular ones that you can use on the margin. Microgrids, semi-autonomous parts of the grid. Increasing two-way flow, that's clear. We're going to have energy going to and from. I showed you that diamond with the energy flows intra and all around. Electric vehicles, that's going to be a big deal. We haven't even talked about that, but there's a lot of implications there. For example, if you have a bunch of people plug into the grid today at lunchtime, there's not enough capacity in the wire to get all those vehicles charged up. So you either need to somehow allocate the capacity using some economic or pricing thing, or you need a fatter wire. So we don't know how that's all going to work out. There's some thought about using the energy in vehicles as sort of like a peaker unit, they call it, to just maybe a few hundred hours a year to help, or 50 a year, 10 hours a year, help the grid out a little bit. If you have a lot of power out there that's kind of plugged into the grid that you can call on, that sounds interesting. I think I read a statistic a while back, I may have this wrong, but if you add up all the power under the hood of cars, it's something on the order of 4 times more than all the power plants. So if we go to electric vehicles, that could be a big deal. Definitely more energy storage for a lot of reasons. We're still going to see energy efficiency. That's not dead. That's the biggest bang for the buck thing that you can do. On the business side, those silos they're just disintegrating. I don't know what to call it. Those guys and gals must work together. They must coordinate. It's becoming much more of a holistic approach to things than it ever was. Competition, especially on the supply side, there's a lot of independent generators out there. Other utilities are competing with each other. End users, maybe if they can stick some of that stuff in, they're actually competing with the utility too. And then there's these third-party energy services or whatever. Solar City is an example, where they'll go around and they actually own the thing and lease it to you, and you get some of the, well, that's competition for the business. Transmission and distribution, it's going to continue to be a natural monopoly because we're not going to put in 2 or 3 or 4 different systems. But what they are going to do is use it to enable this electricity marketplace of the future by allowing people to get access to the bigger part of the grid through the distribution system. This is happening slowly now, but that's going to be a key enabler of kind of a rich, new, more efficient, funner market in the future. So there's that new business model, and I hope they go to pay per performance. I think one way or the other they're going to go in that direction, rather than if you build something and you follow the rules, we'll give you your full rate of return on that. That doesn't give you the incentive. You need to be innovative, to take a little bit of risk, and to optimize performance rather than return on investment. So the profit would be based on this service delivered, not this thing called rate base. And all that is a fancy term for all the equipment that they've installed and that they currently have that they get their rate of return on. That's what the rate base is. So that's everything to the utilities. Investments in equipment. Much greater service differentiation is possible, different pricing schemes than in the past. There's various thoughts about prices that are based on where you are, what time of day it is, what quality you want, how reliable and how green. Increasingly diverse infrastructure. It's just going to be a lot more stuff in there, a lot of different pieces and a lot of smaller pieces. Disruption. I love this. I've been doing this for 30 years, and I thought the disruption would happen 25 years ago, but here we go. It's happening now, and it is kind of exciting. It's going to be slow but steady. It might even accelerate some. But it's both at the technological level and within the business. I mean, their business enterprise has to change to accommodate this new reality, both in terms of their business model and these disruptive technological drivers. Used to be a dirty word, but innovation is going to be critical. Technological processes, financial, how they make money. They may actually have parts of the business operate like any other, where you, at the end of the year, you add up your profit, take your revenue, subtract your costs, and see what's left. They don't do that right now, unfortunately. In fact, anything that's not an investment in the equipment, they call it a pass-through. So what that means is, if it costs $100 million for fuel, that's exactly what the ratepayers, the people who buy electricity, that's what they pay. That's going to change. I think it's going to be really exciting. I mean, I found the boring one exciting just because it was there were so many possibilities. But now, just so many things coming together. I would encourage you to at least think about it. Maybe this is a throwaway statement, but all technical endeavors have at least some business facets. And I always argue to people that basic business acumen is an important element of success for technically oriented careers, partly because opportunities will come to you, or you can find more opportunities because of those business people are so intimidated by the technical stuff. And just between us, I mean, the business stuff is relatively easy to learn compared to the things you're learning. I mean, you got to put some heart into it, and you got to want to, and you have to see how it relates to your technology stuff. But do think about that. So if I had to draw up that nexus with pieces, this is kind of what I came up with. So engineering, you got all different types of that. You got modeling, design, operation, all this technological stuff, smart grid for you guys. It's just, it's exploding, and a lot of possibilities going on here. And then on the business side, this whole idea that the business model's changing, their value propositions are going to change. They're going to be focused on benefits and costs. Their strategies, marketing, sales, all these things are going to have to evolve at an accelerating pace, I think, for this to work. And the legal people, as much as they think they know everything, they still have to work with the technical people to get a lot of this stuff right. Just the idea of setting up a contract with someone for what you're going to get out of their machine, you can't just stick a lawyer on that. And across the board, this environment and sustainability thing is really starting to be pervasive. I mean, if it's not one of the very first things people talk about, when they're done, they'll say, "But what about?" So that's really exciting, and honestly, that's the reason I got into this in the first place. I saw the environment just being ruined. All right, so. Consider augmenting your technical acumen with the basics of key business subjects, and in approximate order of importance: finance, managerial economics, marketing, macroeconomics, project management, and management of organizations and processes. Because often you have to be able to manage your manager to get what you want if you're the technical person. More often than not, it's a bean counter. So computer and communication sciences, I hope it came through how rich the possibilities are. There's so many niches and possibilities, especially if you can see it, the bigger picture, and see how some of these parts fit together. The smart grid alone is just incredibly rich. Power electronics, definitely have a look at these, the power conversion stuff. That's becoming incredibly important. I think there's even an inverter manufacturer right down here in Nevada. I can't think of the name of the company.
Enphase?
I think that's right. Electrochemistry, that's really exploding. You guys aren't chemists probably, but The electrochemistry field is just giddy over this because there's so many possibilities on that side. Whereas before, people used to sort of disregard them. Material science, ceramics, composites, container structures, all kinds of design possibilities for new stuff. Power engineering, don't forget that. Rich possibilities compared to the past for reasons I've talked about. Instead of dumb generators, wires, and transformers, you're going to have a lot of smarts and new technology. A lot of the old folks, mostly guys, are retiring. There's few new ones graduating for a while. It wasn't very glamorous, but I think it'll be fun and compelling and interesting. You need a whole new, fresh perspective, broader skill set. This distributed, variable, modular, smart stuff, that's really scary to people who've thought of it the other way. Just for the heck of it, you might check out the PE requirements for that. And I think that's a really interesting and challenging career field, and I think you could make a pretty good living doing it. So, what did I tell you? Electric utility of the future will differ greatly from the one in the past. A lot of drivers have changed, technology, aging utility infrastructure, I didn't talk about that. It really is getting old. There was a long time when utilities didn't build new stuff. So not only is the new technology coming in, but a lot of the stuff that's in the ground is pretty old. And I can give you specific examples. For example, underground cables. They used, a while back, they went underground with these cables. The neat thing about some of the new possibilities is those things are really expensive because you got to rip them up and then do all kinds of new stuff, put them back in the ground. So if you can get a few more years out of them, that's what you can do with the distributed resources. That's really powerful. Growing importance of all these things that weren't really in the mix before, and there's so many new technologies coming online. I think that's the bottom line from my standpoint. Is aside from the message itself, I think this is something to at least give some thought to as a career possibility, especially if you want to do something that's really accelerating and that will hopefully lead to something positive in the world. So you need that rich skill set, and that's kind of all that I have for you guys. I wanted to get through it quickly so we could talk about any questions you guys would have. Anything else?
Can you tell us a little bit about what you're involved in right now and what your company is doing primarily?
My emphasis is on the value proposition of energy storage. It's a new thing, and no one's really gone through the exercise of figuring out why it's good, what it's good for, how you would evaluate that. Mm-hmm. So it was that's an example of being kind of at that nexus. And I do work mostly with engineers, but increasingly it's the people who have to make decisions about investments in the utilities who are starting to get interested in that. So knowing what it's worth so that you can balance that with the cost. Remember the thing I talked about where the distributed things tend to be more expensive. Well, you need to be artful about piling up the benefits and comparing that value proposition to the more conventional one. So it's in that realm. I don't know if is that helpful?
Yeah. I mean,
and the same goes for all the technologies, including smart grid for that matter.
You had brought up Solar City, and I actually was speaking to a guy from Solar City, and they're partnered with, or sister companies with Tesla, right? So they've got the batteries, they've got this lithium battery they're developing, and he was just saying today that the utility companies more or less are planning on being able to use those batteries, but at no benefit to the end user. And I just wonder, we need to have like an infrastructure maybe where the utility companies have their own business proposition here and they aren't fighting it. But, right now you have utility companies like in Hawaii and Wisconsin, even here in, California, it's always been this way, that are, fighting this tooth and nail and kind of been really prohibitive to change. And I was wondering, what do you see as a way for them to maybe, is there a value prop potentially? Do we see a path forward with them?
Well, there is, but we've got that old business model. I don't want to belabor that too much, but they have every incentive to not do new things. We could talk about that forever. I'm not justifying, I'm just telling you why it is the way it is. Mm-hmm. And one of the things that people don't like to talk about is the transition. I mean, you and I could talk about what a perfect world would be. But we still need to figure out how to get from this old thing, the old stinky utility, to the new fresh, sparkly one.
Mhm.
And that's, I'm not quite answering your question, but the
Sure.
regulators, the utilities, all the stakeholders have to go and sit at the table and talk this through. And the fun thing about storage is it's kind of at the pointy tip of that, because it's
Mhm.
really forcing all the stakeholders to put aside their preconceived notions and biases, because if the utilities don't do this, I like to say they're going to get hit over the head with it anyway. I'm not sure about them being able to use the battery. I don't think the regulators would allow
Yeah,
that.
yeah.
But
Sure.
and
We have a
honestly,
new
right now, I
commissioner
tell
at
people
PUC, right?
if energy storage was free, the utilities wouldn't go around putting it in for some of the reasons I told you before. They don't know what to do with it either.
Yeah.
So my whole thing has been to try to pull that ball of string apart and say, if you do these kind of things, here's what the dollar signs look like for you to do that. And so my purpose in life was to get people to at least go, oh, wow, I hadn't realized that. Maybe I ought to put some of my preconceived notions aside.
Yeah.
And it's going to be pieces like that get us there.
Right.
It's unlike any other industry. Most industries, if you have a better robot and you can double productivity, you'll rip out the old ones and put in new stuff and put in a new process.
Yeah.
The utilities don't do that.
Mm-hmm. Is the PUC, new PUC commissioner, right, just
Mhm.
replaced Michael Peavy? Is he, support? I understand he's supportive of renewables and.
As far as I know,
Yeah.
I mean, I'm not that familiar with his agenda, but I can tell you
Yeah.
at the staff level, there's a lot going on. New York is right now looking at having little control areas at the distribution level for all these distributed resources, which is 5 years ago, that was heresy. The people who control the system were going, oh my gosh, it's already complex enough. And the people down here are going, I'm feeling around in the dark and you want me to run it like a marketplace? So they're going to have to get to that. They're going to have to evolve it, smart grid and so on. So that's just one small example of what makes this so disruptive, messy,
It
very
is
exciting.
disruptive.
Yeah.
Jim, among the storing energy technology, which one is the most common after the battery?
By far, way before battery is pumped hydroelectric. So there's tens of gigawatts. And PG&E owns one of the biggest ones. It's about 800 megawatts. It's down near Fresno. It's the Helms Pump Storage Plant. And they actually put that in when they built the nuclear plant, sort of so that they could take the excess energy from Diablo Canyon and store it there when they, at night when they didn't need it. So they were put together, whatever that was, 40 years ago now, or 35 years ago. But that's clearly a bulk energy thing. And most of what I talked about here, it's the capacity side where the storage provides its benefits.
What about in distributed
Well,
storage?
that's even more capacity because it's
Yeah.
wires, transformers, capacitors, and generator that you're offsetting.
Yeah.
Whereas with the bulk guys, you're putting a lot of energy into it. But you're still offsetting a generator. Now you don't need a generator of that much power with that equal power.
Mhm.
But with distributed, it's mostly capacity related in the sense that it's equipment that you're offsetting. You're probably not going to run a lot of energy through your battery, depending on the circumstance.
Mhm.
Yeah, my question regards solar coronal mass ejections and the risk from that. In other words, the Carrington event, something like 160 years ago or something like that.
Okay.
Quebec a few years ago had a power outage from that. Could you comment on how big a risk that is and what kinds of things that utilities do to harden?
I cannot. I don't think they do that much. I mean, I think it's not regarded as a very likely thing to happen. It's certainly, I think they had that in Canada.
That's right.
Just
Yeah.
20 or 30 years ago or
Yeah.
something. So it does happen. I don't know the answer.
Okay.
There was a solar eclipse went over Germany last week, though, and everyone was hypothesizing that all the solar was going to shut off. It's going to be totally disruptive to the grid, and everything was fine.
What's much, much more likely is that the grid's so brittle and getting old now that it'll have its own problems. So given the probabilities and the stakes, I guess they're probably going to spend more time on that. But if nothing else, all this stuff is a huge distraction. You know, I guess it's sort of like the asteroid thing. You know, we don't think about asteroids when we're thinking about, you know, things that are happening real time on Earth, but that's calamitous. So I don't know the answer.
Okay.
I keep hearing about supercapacitors, and to me, it doesn't sound practical, at least yet. Is the technology going to be reasonable for supercapacitor storage?
Well, Niels Bohr said predictions are difficult, especially about the future. And I used to laugh at flywheels to people's face, and they're really good now. I don't see any reason why they can't. I mean, they're working on the chemistry all the time. There's stuff going on at the national laboratories. And turns out that large bursts of power with relatively small amounts of energy can do a lot. So there's actually a lot of value. For example, you can help stabilize the transmission system, so you can kind of get a few percentage points more throughput on it by just doing some damping, things like that, which you wouldn't think of normally, but that's, so yeah, I'm a believer until I'm proven wrong from experience.
For the energy storage, is it that the distributors now usually invest in this area, or it's also on the generation side?
Well, the generation side, if you will, I like to call it the supply side, has been only these pumped hydro plants, like the Helms one. So it's power plant scale, it's power plant mentality, it's electric supply, pumping electrons out. That's kind of what their business is. This other stuff is in the periphery doing a lot of other things, you know, up and down, maybe dynamic, maybe dozens of times a day, those kind of things. So it really is a different value proposition. Now, that doesn't mean you can't do the other stuff. For example, let's say you put a lot of it in at night, and because you've got wind generation that is in excess of the demand, you charge the thing up at night. Well, now you use it locally, but now you could still use it for some of those other dynamic things that happen at, you know, sub-second, as well as, you know, maybe even ramping up and down as the dynamics change. Did I answer your question?
Well, in a way.
It's all up and down the infrastructure, for one thing.
Yeah.
So the transmission engineers and planners have to think about it. The distribution engineers and designers and operators have to think about it, as well as the electric supply. And that all aggregates up. Whatever this happens here, you know, those all aggregate up to, and then the people controlling the overall electric supply system are going, this is so complex. Supercomputers can't handle that. So there's going to be some fun challenges. And it depends on what you're trying to, you know, what benefit you're going for. For example, if you put it in because your wire is overloaded and you want to defer the upgrade of that, then you operate it one way. And if you're trying to just soak up the extra energy at night, you operate it a different way. So it's a lot of it's yet to be worked out.
You hear a lot about the reduction of hydroelectric, like talk about Hetchy and like various rivers with our salmon repopulation, stuff like that. So it seems like that the hydroelectric is kind of tapering down. Is there anything smart in terms of new ideas in terms of also helping with the water supply?
I'm not sure exactly how to answer that. I would say it seems pretty clear to me that you can't count on the hydroelectric like in the past. And it's happening all the way up into Canada. It's not just here. I'm not quite sure. I think water is going to become a lot more important than the electricity from those things. And it's not just that. I don't know if you read the news about, I think it was a year or so ago, maybe a little bit more, we lost a large nuclear power plant in Southern California. Then they've got these old power plants, they call them once-through cooling, where they just suck the seawater in and cool it off and shove the water out. They're not going to allow them to do that anymore. So the amount of capacity from hydro, from these once-through cooling plants, from the nuclear plant. Who knows what's going to happen at Diablo Canyon? Those things are all going away, and they're not building any huge things like that anymore. So I didn't quite answer your question, but I think they're just going to rely on it less. I don't know what else they can do, and I think there's going to be more pressure on the water side than there will be to optimize for electricity. So it was a good thing in the past, I guess, on balance. But it may be that the heyday of hydroelectric's over. I don't know, did that answer your question? Not necessarily an expert, but it seems pretty clear to me.
Okay, it's now 5:30. If there are no other questions, but if you have more questions, you can of course ask him. But I think the pizza is there, right? So let's now thank Jim Eyer for his really interesting talk. I mean, we